Microplastics are tiny plastic particles less than 5 millimeters in size and are found in oceans, rivers, and even the air. They originate from larger plastic debris breaking down and are also manufactured in products like cosmetics. Recent studies show that microplastics have been found in human blood and placenta, raising concerns about their impact on health. Health risks to humans from microplastics are becoming increasingly alarming, with particles found in lungs, liver, and kidneys. Researchers have detected microplastics in 93% of bottled water brands tested globally. These tiny particles can cause inflammatory responses and are suspected to be linked with cancer and other diseases. Contaminated drinking water is a significant concern as microplastics have infiltrated tap and bottled water worldwide. The World Health Organization highlights that over 90% of water samples analyzed contain microplastic particles. These contaminants raise questions about long-term effects on human health, including potential toxicological impacts. Food chain contamination occurs when microplastics are ingested by marine life and terrestrial animals, eventually reaching humans. For example, fish and shellfish commonly consumed by people have been found to contain microplastics. The bioaccumulation of these particles can lead to health risks, such as organ damage and developmental issues. The health implications of microplastics are not yet fully understood, but they are believed to carry harmful chemicals into the body. Studies suggest that microplastics can lead to chronic inflammation, oxidative stress, and may contribute to metabolic disorders. Ongoing research aims to uncover the extent of these health impacts, as scientists work to understand their potential role in disease development. Toxicity and chemical leaching from microplastics is a major concern, as they can release harmful chemicals like phthalates and bisphenol A into the environment. These substances are known to cause endocrine disruption and developmental issues in humans. A study revealed that microplastics can absorb pollutants from seawater, further amplifying their toxic potential. Microplastics in placenta have been discovered in a groundbreaking study, revealing the presence of plastic particles in the placentas of unborn babies. Researchers were startled to find 12 microplastic fragments in samples from 4 women, suggesting potential risks to fetal development. The presence of these particles could lead to altered immune responses and other health complications for the developing fetus. Microplastics in marine life pose a severe threat as they are found in fish, mammals, and even deep-sea organisms. A study found that over 50% of marine species examined had ingested microplastics, impacting their health and survival. This contamination affects the entire marine ecosystem, leading to disruptions in food webs and biodiversity loss. Plankton consumption of microplastics is alarming as plankton forms the base of the marine food chain. Studies have shown that microplastics are ingested by zooplankton and phytoplankton, affecting their growth and reproduction. This ingestion can result in nutritional deficiencies and cause a ripple effect up the food chain, impacting larger marine organisms. Fish ingestion of microplastics is widespread, with species like anchovies and mullets showing high levels of contamination. A study revealed that 1 in 3 fish sampled off the coasts of the UK contained microplastic particles. This ingestion not only affects fish health, but also poses a risk to human consumers who rely on fish as a food source. Marine mammals such as whales and dolphins are increasingly affected by microplastics, with research showing ingestion of plastic debris, leading to internal injuries and death. Recent studies on stranded mammals indicate that over 60% have plastic pieces in their stomachs, which can cause blockages and malnutrition. These findings highlight the urgent need for effective waste management strategies to protect these critical ocean inhabitants. The bioaccumulation of microplastics in fish tissues is a growing concern, as these particles can carry toxic chemicals that accumulate in organs. A study found that up to 35% of fish in certain regions showed microplastic contamination, posing risks to both fish health and human consumers. This bioaccumulation can lead to toxicological effects, impacting reproduction and growth in aquatic species. Coral reefs are under threat from microplastics, which can smother coral polyps and disrupt photosynthesis by blocking sunlight. Research indicates that microplastics contribute to coral bleaching, with over 60% of sampled reefs showing evidence of plastic pollution. This disruption not only affects coral health, but also endangers marine biodiversity that relies on reefs for habitat. The environmental impact of microplastics extends globally, affecting ecosystems through soil and water contamination. Studies show that microplastics are present in remote locations, with even Arctic ice containing high concentrations. These particles can alter soil composition and disrupt natural processes, leading to reduced agricultural productivity and ecosystem imbalances. Soil contamination by microplastics is an emerging issue, with particles entering soils through wastewater sludge and agricultural runoff. Research has shown that microplastics can affect soil structure and fertility, impacting plant growth. This contamination is prevalent, with studies finding microplastics in over 80% of European agricultural fields, necessitating urgent remediation efforts. Freshwater pollution from microplastics is increasingly alarming as particles infiltrate rivers and lakes, impacting aquatic ecosystems. A study found that over 90% of freshwater samples from urban areas contained microplastic particles. This contamination can lead to reduced water quality and affect biodiversity, requiring urgent attention to mitigate its effects. The impact on agriculture is significant, as microplastics have been detected in soil and crops, raising concerns about food safety. Research indicates that microplastics can inhibit plant growth by altering soil properties and nutrient availability. With over 80% of global agricultural soils potentially contaminated, this issue poses a threat to sustainable farming practices. Microplastics can facilitate the invasive species spread, acting as carriers for organisms across oceans and water bodies. These particles provide a raft-like surface for invasive species, allowing them to travel vast distances. This phenomenon can lead to disruptions in local ecosystems, as non-native species outcompete indigenous populations. Ecosystem imbalance occurs as microplastics disrupt food webs and nutrient cycles, leading to altered species interactions. Studies show that microplastics can affect the reproductive success and survival of aquatic organisms. This imbalance can have cascading effects on biodiversity, emphasizing the need for targeted conservation strategies. Numerous efforts to combat microplastics are underway, including innovations in biodegradable plastics and advanced waste management techniques. Governments worldwide are implementing plastic bans and legislation to reduce plastic production and consumption. Public awareness campaigns are crucial in promoting responsible consumer behavior and encouraging recycling initiatives. Biodegradable plastics are designed to break down more quickly than traditional plastics, reducing long-term environmental impact. For example, some biodegradable plastics can decompose in as little as 3 months under industrial conditions. Researchers are exploring materials like polylactic acid (PLA), which is derived from renewable resources such as corn starch, to replace conventional plastics. Waste management advances include innovations like chemical recycling and improved sorting technologies. A recent development is the use of AI and robotics to enhance accuracy in separating different plastic types at recycling facilities. Studies show that implementing these technologies can increase recycling rates by up to 50%, significantly reducing plastic waste. Plastic bans and legislation have been introduced globally to mitigate plastic pollution, with over 60 countries implementing restrictions on single-use plastics. The European Union's directive targets products like plastic cutlery and straws, aiming for a full ban by 2021. These regulatory actions are supported by economic incentives and penalties to encourage compliance. Water filtration solutions are being developed to remove microplastics from drinking water and wastewater systems. Researchers have designed filters using graphene and nanotechnology that can capture particles as small as 1 micron. Pilot projects have demonstrated that such systems can remove up to 99% of microplastics from treated water. Public awareness campaigns play a critical role in educating communities about the dangers of microplastics. Initiatives like the Beat Plastic Pollution campaign by the United Nations aim to influence consumer behavior towards more sustainable practices. Surveys indicate that these campaigns can lead to a 20% reduction in plastic usage among informed populations. Microplastic detection technologies have advanced significantly, enabling the identification of particles in water, soil, and air. Innovations such as AI-based identification and automated systems are enhancing detection accuracy and efficiency. These technologies facilitate real-time tracking and analysis, crucial for mitigating environmental impacts. Spectroscopy techniques play a pivotal role in identifying microplastics by analyzing their unique spectral signatures. Techniques like Raman and Fourier transform infrared (FTIR) spectroscopy are commonly used. These methods allow researchers to distinguish microplastics from natural particles, providing precise and reliable data. Automated monitoring systems are revolutionizing microplastic detection by offering continuous and real-time data collection. These systems use sensors and AI algorithms to monitor environments without human intervention. Such technology enables the tracking of microplastic concentrations in oceans and rivers, helping to identify pollution sources. Laser ablation is a powerful technique for analyzing microplastic samples by vaporizing material with high-intensity laser beams. This method allows for the detailed examination of elemental and isotopic compositions of particles. Researchers can trace the origins of microplastics and assess their chemical interactions with the environment. Microplastic traps are engineered to capture tiny particles from water bodies and effluents. These devices often utilize fine meshes and filtration systems to isolate microplastics without affecting marine life. Innovations in trap design are improving efficiency, allowing for the removal of up to 95% of microplastics in tests. The AI-based identification of microplastics is transforming detection capabilities with machine learning algorithms that can analyze samples faster and more accurately. These systems are capable of processing thousands of images per minute, identifying microplastic particles in various environments. Researchers have demonstrated that AI can increase detection accuracy by up to 90%, significantly enhancing monitoring efforts.